So where we left last time is something called hierarchical scan. So what we said is that rather than having a fixed set of window to work with, why not create a smaller set of windows, and these windows obviously this white square region I call a window, and this corresponds to what the neuron is going to act on. Okay, so neuron will take all the pixels in this white small box and then do a linear combination, right? That's what neuron does. So so each neuron will now only act on a smaller window, and then the idea behind hierarchical scan was that in this example, first neuron might scan this this region, okay, this bigger white box, and then similarly the other neurons will also do their own scanning of the within the bigger white box, and then this is later used to make an inference or like decide on this white or big box by the next level neuron. Okay, because this first neuron, it acts here, it produces one dot, second neuron acts here, produces another dot. I mean the first neuron itself, this is for the first neuron, and the first neuron again acts on this, produces this box dot in this, and then it acts on the fourth one and it produces that that one, right? So here these four outputs that we see is the output of the first neuron. It did a W transpose X, so X are the pixels here, and W is the weights of the neuron, and so it did W transpose X, and it produced one value. Okay, W transpose X is just one value, obviously, and then the same neuron went here and did another W transpose. You got this second dot here, and then you did the same first neuron again. It did W transpose X here, it got this, W transpose X here, it got this. So it produced this four output. And similarly, the second neuron also did the same thing, but the thing is that second neuron is acting like a different type of filter, because second neuron has its own set of weights. Okay, so it's like you want to have multiple worker trying to work on this region to identify in different features within this white box. So that's why second neuron is also used, and second neuron also applies does this W transpose X again, it does here, here, here. So that's how second neuron also produces these four outputs, and similarly the third neuron also produces the four outputs, and the neurons here will now act on these. So here also we are trying to have two neurons trying to infer on these four outputs. Okay, so as I said, we want to have multiple kind of workers, you can think of neuron, trying to decide in different ways what could have been in this white box. So this is the output, this is the output of this neuron, let us say, and this is the output of this neuron. So this neuron will now look into these, okay, and it will do the linear combination again. Okay, so it has its own weights, so and then it will produce one output here. So basically this output now, if you see these four dots, it corresponds to this bigger white region, obviously. So this one dot now seems to be like trying to infer about this big white box, because this small box, small dot came from these four dots, and these four dots corresponds to this white box. So essentially it's trying to kind of make use of the three different interpretations by the three neurons on this bigger white box region, and then it's trying to make a decision on that. Okay, so this way then the process repeats basically. Then you will go into this region here, and then again each neuron here will produce the four dots again. So these four dots will be somewhere here, and similarly second neuron will again produce four dots here, four dots here. Okay, and that will be for this region, obviously. So then the process will repeat in this box. Okay, and then the four dots will be produced, and the process repeats, and then the one dot here, this guy, will be responsible for deciding on this box. Okay, and again similarly this dot will be this neuron will be giving another opinion. Okay, so there are two opinions given by these guys here, and then finally, based on these two opinions, the final neuron will decide whether the final flower can be said. We can say that there was indeed a flower based on that. Okay, so again, this neuron again might to cover the whole region, this might need a couple of entries like that from here to infer something finally from here. So because 1 dot corresponds to 4, okay, and so if you take the second dot, then so 1 dot corresponds to this. So if you consider the second dot of this guy, it will correspond to this. If you consider the third, then this is this. Fourth, then this is this. So basically, if I'm not wrong, 4 dots of this guy is kind of trying to decide on this yellow box. Okay, 4 dots is responsible for whether the flower was written in yellow box. Okay, so this is why we call this hierarchical scan. Okay, because this smaller level filters are trying to capture small features, and then bigger, slightly higher level neurons in the next layer are trying to interpret the bigger region of the image, and so on. Finally, a whole conclusion is made on the final image. So this is hierarchical scanning, and as we said, we can do this at multiple levels. Okay, so in this case, you can do it at multiple levels. So here in this case, again this hierarchy could be first level and then second level, and this is like the third level. Okay, so in this case we can think of this as three level hierarchy. So hierarchy itself can be developed in multiple ways, and finally this dot here is deciding on this portion of the image. Okay, in this case it's supposed to learn a flower detector. Okay, so when the scanning is happening, when the scanning is happening, obviously these are neurons, right? So these neurons do W transpose X, right? So here, if I see here, so these X could be the portion of your image, and W is the weights of the weights of this neuron. So this is W transpose X plus some bias term. So obviously, in a supervised learning, you will have a label that's saying that there was a flower here. Okay, so based on that, these weights will be updated. Okay, and it will be forced to learn these weights and eventually say that there was indeed a flower. Okay, so all these weights, when we say that neuron is scanning and all this, obviously this is a parameterized network, so there is a W weight involved here. These are parameterized networks, obviously. So these weights will be forced to learn. And as I said in the last class, once the filter moves, because this same neuron will be scanning this region here, so obviously the weight are shared. Okay, so that's what we said in the last class. So this weight again is the same weight, and but now your X is some second. Let us say this first one was this. So your X is X2 here plus some bias is B2. Okay, so these weights are shared weight, and based on the feedback from the loss function and so on, we will try to update the contributions from the both. Okay, so this is the case of the this is why we call this a shared parameter network. And as you have seen in the last class, by updating the weight, we mean that del L by del W1 plus del L by del W2. Let us say this is W2, this is W1. So basically, this is how the weights get updated. But we are not bothered with the training phase right now, because training, except for one or two generative modeling idea, usually training is not a prominent thing to look at for the moment for us. Okay, so we can skip that. So this is how hierarchical scanning can be built. We can do this at multiple levels, and finally, yeah, so this is so these arrows, as I've said in the last class as well. So basically, as if we can think of these as so we have changed the figure. Now we have 2 neurons. So as if we can say that the neurons, there were like multiple copies acting on these. So then in this case is 4 times 4, 16. So each neuron was acting on 16 region, and but the fact is that the same neuron was acting. So another view that usually helps in training is that as if I applied the copies of the same in each of these 16 small square regions, and that will help me during weight update phase, the view that this was a shared parameter network. So when I'm updating the weights, I am supposed to kind of add the contributions from each of these weights. Okay, so if you want to really know about explicit details about training, you can do so, but for our course it's not really needed right now. Okay, So all this we saw in the last class, and then in the hierarchical scanning, this is how it happens, and finally a decision is made. Okay, so and in a compressed form, we can also see let us say 1D. Okay, so the audio data that, if you can remember, then scanning is like we break this down, in this case 1D, so it would be chunks, okay, 1D chunks, and then if we look at our very original scanning procedure, which was non-distributed, so we always had a fixed chunk, and then that whole chunk goes into first neuron, and then processing happens by the, so these are all the neurons in the first layer, all the neurons in the second layer. So we have denoted it in a very compressed form. So this is non-hierarchical scan. So obviously this is what we started with. Chunks were fixed, and then the same processing is done on the same chunk throughout in the higher level, and then finally you decide. Whereas in hierarchical scanning, we break that like this. We go for the smaller chunk scanning, and then these smaller chunks are then referred to next layer neurons, and then this neuron is now deciding on this bigger chunk, and so on. And again, we can build more hierarchical levels. So in this case, it's like 2 level, this, and finally this is just looking at this. It's not taking anything from the others. So in this case, it's like a 2 level scan, and this is a distributed scan. Okay, so so again, this is again same thing we saw. We just kind of recalling that. So we take an image segment in a 2D, and then we pass it through MLP. So this is like the usual. Okay, and then yeah, we can y, and then yeah, so we change the loop, I guess. Yeah, so we change the loop to xy being at the top. So that's how, like, we can think of hierarchical scanning, where we fix kind of the chunk, and then we are working on the smaller chunks. So later what we said in the last class is this is what finally we get after all those changes in the loops and so on. And this is what we call a convolution loop, where xy is there. So you can just look into the shaded region, and that's what we define. So fix a chunk, and then go through the application of these filters on these. Okay, and so that's how we define the convolution operator. Okay, so we can do vectorization and things like that. So we can kind of put the weights in a vector form. So in this case, we did the I loop as well, I guess. So that I loop is now taken care of. That is removed, and that I loop is now vectorized here. So there you can see WLI was there, but I was like the number of pixels I was scanning, right? So number of pixels I'm scanning, I can take this as a vector. So number of pixels I'm scanning, take that as a vector. So that is the pixels that I'm thinking of, and this is the segment that I'm working on. So obviously the weights correspond to the number of pixels, because I want to do the linear combination. So that I loop has been thrown away. I don't want to go pixel wise. Just take it as a whole chunk, which is a vector in this case. If it's 1D, if it's not 1D, if it's 2D, then it's a matrix. And in fact, it seems like it's even 3D in this case, because the channel has been introduced as well. So it's like go through all the channels as well. If you have a difficulty in viewing the channel, then I have some more slides which will make things clear. But for the moment, you may forget about channels. Let us say this is one channel. So basically, one channel means like one matrix of pixels, which can represent grayscale images. Okay. When you go to color images, then you have 3 channels RGB. So we will come to that. We will see the final form. So this is a vectorization going on. So just made that into vector, and so that's the algorithm. And then distributed scanning helps in reducing the number of parameters. So there is some calculation going on. I will try to avoid going into this calculation. These are simple, but still it may take some time. So I will leave this as an exercise for you. Everything is there in slide. Nothing is coming from outside here. So these are parameter counts. Okay. So so basically number of neurons and the dimensionality of the input and so on, number of neurons in the second and so on. You can count this, and what would be the total number of parameters? By parameter we mean the weights of the network. Okay. So in the distributed non-distributed scan, you have this many parameters, and then if you go for the distributed scanning, then please check as an assignment that there will be a good reduction like this, 2D and 1 and so on. Okay, so let me skip these things for the moment. So these slides are left for you as an exercise. You do this because there is a reuse of computations. Okay, so this what slide is saying, that some of the computations we kind of, in a distributed scan, you can reuse some of the calculations because that neuron kind of previously computed that and so on. So all this helps in the distributed scan. So I'm going to skip those for the moment. So these are like parameter calculations. Again, you do that as an exercise. In the 2D case as well, what will be the parameters? All the details are there. Okay, it's okay. So then we understood convolution. Okay, so convolution as such is nothing but each neuron comes with its own set of weights, and it starts scanning small window sizes, and it could be done in a hierarchical way. So these are the two main things we have seen in CNN so far. But then there are few notations and a few changes also, which are minor changes. So this is also called filter when we scan through these. In fact, I have been using this word already. And so this scanning these area, these windows with the neuron, which is coming with the same proportional, same number of weights as the pixels in the window. And so these are called filters. So these neurons actually are filters. Okay, so so that's the terminology used, filters. And then there is something called receptive field. So receptive field you trace back to the original image. Like let us say you are here, then what exactly it might be corresponding in the original image. So as we have seen before, right? So these first level neurons are looking at the smaller rectangular region, right? But then if you go to the second level neuron, like these guys, then we know that these guys are looking at the bigger region. So this is the receptive field of these neuron. So this neuron is looking at these boxes. So for which the receptive field is, I believe, this region, and this neuron receptive field is even bigger. Okay, so that's what we call receptive field. And then we usually use fully connected networks, which is something I already discussed last time. So you may final outcome could be, let us say you have this bigger set of outcomes from this region. So let us say you divided this perhaps like this. So then you may want to kind of infer from these outcomes finally. So this becomes a classification problem, that whether the image was there in one of these okay, which were until now these were identified by, these features were extracted by these final layer neuron, and finally it's a classification problem. Okay, so then you can say whether what we found as a feature, do they combine together to give me a flower or not. So it becomes a classification problem then. Okay. So that's the idea of fully connected network. So usually in a CNN for object detection, usually your final set of layer is fully connected network. There have been some changes in that idea as well, with the ResNet and so on, but we will see that later. But usually this is the thing, convolution layers, and then finally followed by fully connected layer. And then the obvious thing to see is when I'm scanning these areas in the image, how much stride I will take, right? So stride here means that when I'm going to the right, how much right I should go, right? So if I'm going in a way that I never overlap with the previous one, then there will be like non-overlapping, right? So then my next set of scan is this. So I never overlapped with this guy. But usually that is not a good idea, because it may happen that there was something interesting right in the overlap, which neither of them could see because they wanted to not overlap. So having no overlap may be a bad idea unless you have very small level filter and then you have high level filter. So in that case, interesting features will be captured by very small level filter. But if not, then having no stride can be a bit problematic, because you might miss the features which are in somewhere here. Because if the features are somewhere here, then neither of the scan gave you a full probability of detecting something interesting there, and you thought there was nothing there. But it may happen that exactly the overlap region had something which could have given you maximum probability of finding something. So in this case, one is to be a bit careful. Again, it depends. If you are working with very small filters, then those will capture anyway. So how much to stride? Okay. So how many pixels you want to go left? And similarly, once you scan the full row, then you have to come down. So how many pixels you are going to go down? So these strides, these are called strides. Okay. So stride may be greater than 1. Okay. So one possibility is that that you are very cautious and you only leave 1 pixel at a time. So maybe you are going like this. You just left 1 pixel as the first column you left, and then so you may do that. But stride obviously can be greater than 1. It can be 2 pixels. So these can be sometimes hyperparameter. You have to play around with these things to what is best for the given data set. So obviously, if you have slides a lot bigger, then you are saving computations, obviously, because then if I have only one stride, then almost the number of computation is almost equivalent to number of pixels in the row. So it's like you are not really leaving anything out. But if you had a bigger stride, then you will finish this row in a less number of steps and also less computations you are going to do. Okay, so there is a trade-off how much stride you want to do. And when you do take the stride which is bigger than, let's say, 1, then there is a shrinkage is a lot more. Okay, so in this case, let us say if this was the image, then if you don't if you let us say the stride is 4. Okay, so in this case, more or less, you will reduce the row dimension by almost by 4. Okay, so because you will reach here like 4 times faster compared to just taking one stride. Okay, approximately. So having more stride naturally leads to less leads to reduction in the size. Okay, reduction in the size, right? So if your goal is to kind of reduce the next set of outputs, then you will take stride which is larger than 1. Okay, so this could be stride greater than 1 could be seen as a sub sampling step. Okay, but there are other ways to do the reduction in the side. So if you want to include the stride, then explicitly other than 1, then you may go with this. So this is the for loop for the x pixels, and this is the for loop for the y pixels. So this is saying like how much stride I want to take when I'm moving to the next set of x. Okay, and similarly here this is the stride for the y. Okay, so it's saying like how many pixels I'm going to skip. Okay, so this is more or less already everything is the same. It's just that we change the stride, and you can change this in the code. Okay, so right. So another modification in CNN is something called pooling, and pooling is could be we call it sometimes max pooling, and sometimes we also go for the mean pooling. So what we do in this case is that after the convolution output, we look for the maximum entry in this. So let us say this many entries were there, we just take the maximum out of that. Okay, so that is max pooling, and then we could have also taken a mean of these guys, and then that would be mean. So you just take an average of these outputs, and that could be the mean pooling. Okay, so this is also, as you can see, this can also reduce the dimensionality of this input, because all this inputs here kind of reduce to 1. Okay, and then max pooling also depends on stride as well. So how are you doing the max pooling? So you are doing max pooling here, and the next step, do you want to overlap like this, or you don't want to overlap like this? We will see some architectures, recent architectures, what they are trying to suggest, what is the good practice. But again, max pooling itself has to be done over a window, and then you want to see. So if you don't overlap, then obviously reduction will be great. Okay, so it's like big, I guess. So all these guys will reduce to this, and the next set of window is this. Here max pooling will just reduce to 1 dot. So this way we can see that max pooling can actually reduce the dimension. So here there is a small example. So this is the output, let us say, after scanning with whatever weights you have, because you are also training, right? So these weights keep getting updated. So let us say initially you start your network with a random weight. So after applying random weights, let us say you get some outputs 1, 1, 5, 6. So this neuron applies this random weight on some small window here. It produces this output, and then if you do a max of these entries, then obviously you get a 6. Okay, so that way so max operation could be seen as another neuron. So that's like another view that It's a neuron that just does the max operation. Okay, so this is how max pooling will progressively give you new values. Okay, so again, it seems like looking at this, it seems like it produced 3 outputs. So it seems like it was with stride 1. Okay, so first would have been like somewhere max pooling of this guy. It produced 6, and then there was this guy, and then finally this white box that is on here. So it seems like there was with stride. Okay, so again, depending on the stride, the output will be reduced. So in this example, we shrank the image after the max. The stride was the size of the max operator. So there are like various illustration of, in this case, it reduced to 4 basically, okay? But earlier it scanned 16 outputs, reduced to 4. So there are like various ways we can take strides and reduce. Here also I see a reduction here. Okay, so again, this is again for max pooling, again an example over this whole set of images. Yeah, so what happens with the next set of convolution layer? They work on the max pooled maps. So obviously, you can do convolution, then max pooling, and then start with convolution again. Okay, so this process kind of continues for several steps. Okay, convolution, max pooling, again convolutions, again max pooling. You may do multiple convolutions, then max pooling. Okay, so how you combine them, it's up to you. Okay, depending on the problem at hand. And finally, you can see this fully connected layer at the end. Okay, so these are okay. So this is the network produced by Jan LeCun. So he proposed this architecture for handwritten digit classification, and we may say that CNN became popular after this. Okay, so when he proposed this architecture, and so this was used in applications for automatically kind of detecting the handwritten digits. Okay, so so this is what he proposed. So this is for handwritten digit input image is 3, and then this is the first layer, convolution layer. Okay, and input is 32 by 32. So that's the input image dimension. So this is a 32 by 32. That's the number of pixels, and then he applies filters. So this is called first layer filter, and he have, if I'm not wrong, 1, 2, 3, 4, 4 filters he is applying on these images. Okay, so each of these 4 filter obviously will produce their own outputs, which is captured by 4. So remember that the number of filters you apply actually decides the number of outputs that you're going to get. Okay, so but if I would have increased the filters in the next set of scan, then obviously the output changes again here. Okay, so here the fact that I applied 4 filters, obviously the output will be 4, but then here I have opportunity to change the number of filters. Okay, so number of filters as such are like neurons. Okay, so it's like you increase the neurons here. Okay, so here yeah, so if you scan these, then so these outputs by the filter are called feature maps. Okay, so there is an intermediate step that has been indicated here. So first apply the filters, then you produce an output. These are feature maps, and these outputs are again processed by another set of filters. Okay, but it seems like there are a few more things are going on here that I might be skipping here. So here there is an input. I see there is an input, and then the first layer filters. So this is like convolution layer. And then there is a subsampling here going on here. So it's like kind of hidden here a little bit. So subsampling has been done. So you see 28 by 28 now reduced to 14 by 14. Okay, because some subsampling was done. It could be max pooling. The subsampling, as I said, could also happen because the strides taken by these guys were larger than 1 or maybe 2, I guess. These guys take strides of 2, then it will reduce the output features by half almost. Okay, so it may happen that this was subsampling done by the stride itself or by max pooling. Max pooling can reduce 4 inputs to 2 also. So to 1, right? So yeah, so and 2 by 2 to 1 basically. Okay, so and then so these are the outputs produced, and then we have another level of convolution going on. So in this case again, another I don't know how many are there, but these are like yeah, 5 by 5 convolutions are there. It's written here. So these are 5 by 5 size filters. Okay, but there are many of them now. Okay, So then they produce these feature maps. So basically, after applying this, we get so-called feature maps, and then subsampling is again applied. Okay, so C for convolution, S for subsampling, and then finally the output is fully connected. Okay, fully connected layer. So that you make this into whole vector. Right now these are square chunks, but then finally you make them all this into one big vector, and then it goes into usual multi-layer perceptron, and then it decides which of the digits it could be, 0, 0 to 9. Okay, so this is the original architecture, and that's when things became interesting and people started taking this into seriously. So let us put things together and see what exactly happens even in the color images. Okay, so then you will have a full idea of the real case CNN. Okay, so there is an input image here, and there is convolution layer, and these are the filters we can think of. And then we usually do downsampling via convolution, via max pooling, min pooling. Okay, so we know a couple of ways to do downsampling. Then we apply convolutions. So and then we do downsampling. When we do convolutions, downsample, and then finally it goes to multi-layer perceptron. So this is more or less what a CNN network in a broad view, high-level view, it means. So obviously convolution layers comprise of neurons that scan input, downsampling layer perform max operations, and then the two may occur in any sequence if you like. Okay, you can do them in any sequence depending on the problem at hand. Okay, so convolution layer, as we have seen, they are learnable, right? By learnable we mean that there are weights that can be updated. So we know that these filters, these are basically neurons, and the neuron come with their weights. And obviously, looking at the level, we build a loss function, and then if the loss is high, we do the gradient and move in the direction of the negative gradient, minimize the loss. So all this have this. Usually downsampling layer, or let us say if the downsampling layer is kind of like max pooling or something, usually they don't have weights. Okay, so as you have seen in the max pooling layer, I have output of let us say 4x4 4 entry output. We just take a max. So this is just a max operation with no parameters involved. Okay, so there is no weight involved usually in max pooling layer. Okay, so convolution layers are learnable, and then finally the fully connected layer is also has weights. Okay, so the weights during training, these are the weights that matter. Okay, that you will try to update. Okay, so in general this is what happens. Image itself or the previous layer, like if we look into a very generic way convolution works, is that there is a previous layer and there is a convolution layer. The convolution layer acts on the previous layer and produces some maps. Maps are basically outputs after applying these filters on the previous layer. Okay, so this is what is happening. Is there are convolution layer has multiple this filter, and the first one will act on these, and then it will produce some output, and obviously activation also happens. Okay, so we should not forget that after this linear combination, the one more interesting step is activation. If you don't do activation, then it would be a fully linear network. Fully linear network are not very expressive. Okay, so activation plays an important role. What kind of activation usually people do now? It's ReLU is very popular. So this is more or less the step. Convolution is just dot product, but then there is after dot product there is an activation as well. So this is what usually it means. There is a filter which is the neuron, and neuron weights are like this. In this case, we have just, for example, we have just said, let us say those weights are 1, 0, and so on. Okay, and there is obviously there is a bias term as well involved, and then this is what it acts on the given image. And then final output, we call it a convolved feature. Okay, so this is something we have already done. I don't think there is much to say here. And so if you see what is going on, so that's again similar view is just scans like this, and that produces the first. Now the second neuron is active. Now the second neuron is scanning the region again. Okay, just like the first neuron, and then it's producing its own output. Okay, so the one way to see is like filters themselves have the same shape as the input tensor. Okay, so we can think of this as tensor because it's a color image, right? So color image essentially comes in this RGB form. So a better view is a cube-like view. Okay, so this is like this. Okay, so basically the image is like this, which is red, green, blue. You combine RGB red, green, blue to get some color pixel. So essentially, this flattened view is sometimes not very clear. Okay, so that's why it's better that we look into this kind of view, where we call it a stacked view. So let us say the kth layer output are outputs like this. There are k matrices produced. Okay, then your filter is also, you change the shape of your filter also to match those many outputs, okay, of the kth layer. Okay, this way you can see that filter will apply like this on each of these. Okay, so so one neuron filter is now of this cylindrical shape. Okay, this is just for one neuron only. Okay, one neuron. So one neuron is coming with this own cylindrical shape that will match the scanning area, which is also cylindrical shape. Okay, because now when we are working with color image or any even high dimensional image like hyperspectral, right? But for the moment we stick to just color images. So in this case we will be dealing with 3, let's say. So you see, you have changed your filter shape to match with the with the scanning area. Okay, so this gives you a slightly better view of how things are. So this is how things are. Okay, so in color images, this is what you are doing. This is your filter 1. Okay, this is your first filter. Of course, this filter itself has multiple stacks like these yellow things. Okay, and each have their weights. Okay, it's not like shared weights. So each have their weights, but they apply on the first stack of the filter applies on the first stack of the input. Second stack of the same filter applies to the second stack, and so on. Okay, and then they produce one output. Okay, so if you look into the notations, then P here stands for these number of planes. Okay, so what is happening as a final output, you also kind of add these values. Okay, so if you fix a plane, so let us fix some plane, let us say P is 1. If P is 1, then this guy is 1. Okay, then WS and KL. Okay, so S stands for neuron. Okay, so I will correct if I'm not. So neuron number, which neuron is scanning this. Okay, because this is just the first filter that is doing its job right now. So this is, let us say, first neuron. First neuron acting on the first plane. Okay, and it is scanning the pixels which are denoted by KL. So K and L, this is L by L. So L, it goes L horizontally and vertically. So this is denoted by KL. So goes from 1 to L. And obviously this L will keep changing next time. So what is happening now is the weights of the first neuron acting on the first plane. Okay, so basically this itself is different weights than this or this. Okay, that's what you are saying. So this because plane changes, plane becomes 2, then your weights are for this. Okay, so these, each of these weights are different. So plane 1, neuron 1, and acting on KL window pixel. Okay, so this is working on this this Y, and YP equals to 1 means that this is our Y1, the first plane of the output. So this whole thing is Y. This whole thing is Y. The first slice of this is given by 1. Okay, so this is what is happening here, and more or less the for loop is kind of, so these are the weights, and these are the segments, and this is the bias. Each neuron will add its one bias. Okay, so S1 is the first neuron, S2 will, so, and then whole sum you will take over the plane. Okay, so you do this for the first plane, you do this for the second plane, you do this third plane, and then you sum it. That's why you have a sum P, right? So that's what it's saying. Okay, convolution map at any location sums the convolution output of all the planes. Okay. So the view, if you think about the view is more or less clear that a neuron now is coming with its own cylindrical shape, and because the input is also kind of cylindrical, so it has modified itself in the same way so that it's easier to kind of do tensor product, inner product, right? So this is our first neuron. It has different weights, and it's acting on each different windows simultaneously for all planes, and finally you are combining this. So as if you could have made this into a very high dimensional tensor in your product. Okay, so this guy you could have taken this as some tensor T, and this guy you could have combined this window where you are acting as some Y tensor T. So this whole thing could be seen as tensor in a product. Okay, so this is what is happening now. It's a question of just moving around, and various outputs will be produced. So this output that I see, this is for the sth neuron, and that's it. Yeah, this is for sth neuron, and the corresponding output. So I and J decide the window, right? So I and jth window, and for the first neuron output. So basically this guy. Okay, so this is filter 1, and it's producing, in this case it's 1 1. Okay, so the output 1 1 and then output 2 2. So the whole effect of one filter applying on an input which is tensor is just a matrix. Okay, so the shape of the output is a matrix. Okay, because you combine everything and produce one output. Okay, so then it moved to this area, and then it produce another set of outputs and so on. The formula and all this just changes with the Y. Basically, you need to change, and the weights of course, because no, not the weights. Sorry. So so here it's the same neuron just moved, right? So the weights is the same neuron acting, so weights remains the same. Because if you see here, S is the same. It's just that now it is acting on the new area, a new region it's acting. Okay, so okay, so that's more or less what is happening. It keeps scanning like this. Okay, and finally it produces all the output. Okay, so this is what happens in code. So and now W is a tensor, right? So that's what I said. So W is a tensor of basically kind of K1 by K1 would be, yeah, K1 by K1 is your window size. So here if you can see, K1 times K1 is the window size, and this is telling you how many planes were there. Okay, so dl minus 1 I believe is the number of planes. So this is obviously W is a cylindrical. That's what we saw. So dot dot dot, let us say like this. So this dimension I believe is L minus 1, and this filter sizes are K1 times K1. Okay, so this is how it's working on K1 by K1 patch. So we believe that the input Y obviously should have similar DL minus 1 dimension. That's why I need DL minus 1 of these stacks for the filter. Okay, so that's it, more or less. It's just that it's a cylindrical view now, but more or less what is happening is the same. Now this is the tensor product that is happening here. So segment itself is a tensor of this dimension, and W is also of the same dimension. Okay, that's why they can do inner product, right? Inner product happens with the same dimension, right? So the input segment is your cylinder, output tensor is the filter is also a cylindrical shape of this dimension, and then you just do this tensor inner product. Okay, so this tensor inner product that you see here, and then after that you have to do, because after inner product, regardless of the dimensions, okay, it always produces single value, and then you do an activation function, okay, scalar activation of these, and then finally you save all this, and then you can do the softmax activation and so on. Okay, what happens to the size of the output, right? This is, again, we have already done this. I guess this is now very simple. So if the input size is 5 by 5, this is like an exercise. So input size is 5 by 5, filter size is 3 by 3, and stride is 1. What would be your predicted filter size? So it's quite clear that it's 3 by 3. In 5 by 5, if I move 1 pixel each time as a stride, then this is the first scan, this is my second scan, and this is my third scan. And I don't want to fall over, right? Okay, there is a change that we can do with some padding and so on, but so far what we have understood is that we don't want our filters to go beyond this, okay, because there is nothing there, right? So with that view, where we don't want to fall over while scanning, then I can go only three steps, so 3 outputs will be produced, and since this is squares, 3 by 3 outputs will be produced in this case. Okay, similarly you can think of, what if 5 by 5 and the filter size is 3 by 3 and stride is 2, then in that case obviously if you don't want to fall over, then it's 2 by 2 output. Okay, And in general, you can write down a formula that image size is m by n and your filter size is m by n. Then it's an easy exercise to and if the stride is 1, obviously, okay. So if the stride is 1, then you end up into n minus m plus 1 times n minus m plus 1 output, okay. So as you can see, okay, if you increase the stride and so on, then yeah, things can contract. So far what we have assumed is that we don't want to go past the edge, okay. We don't want to fall over, but yeah. So if you really wanted to also go past the edge, then you have to do zero padding. So as if you are saying that there is nothing outside this. So in that case, obviously, if you take stride 1, then with zero padding, I believe you will get the same output, because now you have zero padding, right? So it can kind of start with, if it's 3 by 3 or something like that, you can check that the output will be also kind of 3 by 3, or in this case it's like 5 by 5, okay. So you can check that output will be also 5 by 5. If yeah, so zero padding could be done, okay. That's one possibility, and we could have even done this with the 4D. I mean, if you don't take the J, right? J stands for the neuron, right? So I could have done this because all the neurons are supposed to scan the same segment, okay. So that can also be vectorized. That's what it's trying to say, okay. Because if I have an image, which is like this, then I have multiple filters, okay, like this. Now all these multiple filters, they act on these, right? So this filter F1 acts on this, but this same filter F2 also has to scan the same area, and filter F3 also has to scan the same area. So the idea is that this is your neuron 1, J1, this is J2, and this is J3. So can you not combine this and then apply this on the segment, okay. So that could be done, but in this case the thing is that the segment is 3D, but the tensor the W I have combined, or I have stacked them all together, so that the W is a 4D. So 4D is being applied to 3D, so the output will be a vector in this case, okay. So there is a vectorized inner product you can think of. It's a vectorized inner product, right? Because it's like as if you apply matrix times vector, okay. So you know that you want to do inner product with 2 vectors, right? But when I do matrix times vector, then it's like result of the first inner product, and then matrix times vector result of the second inner product, and so on, and then the final inner product, right? So it is in that sense, okay. So in this case, 4D tensor is applied to 3D, then I mean it's like an inner product. So each slice of the 4D is if you remove one of the dimensions, right? So basically the neuron, okay. So just take so this is your first slice, okay, which itself is a tensor, is a 3D tensor. This is a 3D tensor. So the 4th dimension is across the neuron, right? So what we are doing here is that take the slice, okay, slice in the sense that the 3D tensor corresponding to the first one, and then you can do dot product with the 3D input, which is y, okay, and that gives you one output. So you will get one output, and then you will pick the second filter, which is 3D, which gets multiplied with 3D, and it produces one output. So this way you can say that this Z is this vector now. That's why it's written in bold now. And then activation also you will do pointwise. So for each entry you do activation, so output will be also a vector in this case. So what we have done is that we have vectorized to the maximum possible extent that we could, okay. So the W is like as much, because you can only go that far, okay. That is the best you can do. Each filter is acting on the same segment, so you can vectorize until so many filter. Beyond that you cannot do. Then next layer neuron has to wait for these guys to get completed, right? So these things are good because there are, as I said in the last class, there are like very interesting libraries like BLAS3, BLAS even for tensor now, there is an extension. We were saying BLAS3 when we do matrix times matrix operations, then it's like BLAS level 3. So it's like very good in cache and so on. But then if you are working with tensor, then it's even higher level. So it should benefit as such. So so this is the best algorithmically, and it's also very compact. So this is what happens, right? We are kind of repeating this again. This is the picture. We have convolution downsampling and so on, and we have also seen the algorithm. In reality, the input image is a 3D tensor. If you are working with colored image, if you are working with hyperspectral image, then 7, 10 dimensions. It depends. Okay, so in general, you can generalize these ideas. These input, we just see this as a tensor in the abstract form. However, how many channels are there determines the dimension of the tensor, the third dimension of the tensor. So so more or less, not third, but I mean, if it's high dimensional, then obviously more, right? So convolution downsample and so on, multi-layer perceptron. So that's it. So that's more or less. And this is something I also did in the basic CNN thing. So since this is my next talk, so I am kind of repeating this, the detail case, but this is repetitive. So we just did all this. And in reality, it's like this, right? You have color images, RGB, and the filter that I want to use on this, the first layer filter, there are, let us say, K1 number of filters. Okay, so there are K1 number of filters. Right, and in this case, K1 will be 4 in the figure. If you see explicitly, there are 4 filters I want to start with, and each filter size is a L by 3. Okay, so basically the input has 3 channels, so that decides this third dimension of the filter. Okay. So parameters in this case, and this could be kind of a hyperparameter, right? How many filters to choose, no one really tells you. Okay, so this is something you start with on your own. Okay, whatever suits you better. With the compute resources also play a critical role in how many filters and dimensions that you are going to choose. So K1, so parameters to choose in this case is K1. L is the patch that you are going to scan, and S was the stride of the convolution. Okay, so so these are the parameters, and total number of parameters, if we count, then this will be obviously K1 times 3 L square, and then plus 1 for the bias as well. Okay. So these are the again seen in a slightly different way. This is how the outputs are. Okay, where the filter is the first filter output is like this. This is first filter output. So, and then this is the second filter output. This is for third filter output. Remember, the filter output is like just the matrix. Okay, so this is the first filter output, which is the matrix. Second filter output, third filter output. So for color images, we had this separate notation being used here. So now instead of planes that you have seen previously, now we say that these planes are like RGB. Okay, so this sum is over the RGB. So this is like C here, right? So C is RGB, the channels, right? So we that's the specific case here, color images, and this is the these are the weights, and on which channel the weights are applied. Okay, so this is more or less what we have done. Is the same thing being done here in a very specific case of RGB. So so these are the weights, and this is like the which neuron, like M is like the neuron. So if you fix M to be 1, then this will be W11, and which will correspond to the outputs that you get here. Okay, because finally Y11, M is 1, then this guy is finally your this output. Y M equals to 2, this means the second neuron. Okay, and then this output is here. Okay. So I hope it is clear. This is more or less what happens. Okay, and then we can do pooling also. So we have also seen this. We can have this max pooling and so on, and then we are supposed to find the index with the maximum entry. Okay, so these are some simple calculations. I believe that's not a big deal. Yeah. So max pooling also the way you do, right? What is the pooling stride that you pick, that kind of like reduces the dimension. So obviously, if your stride of the pooling is d, then the output image becomes 1 by d roughly. You have to take a ceiling or floor, I guess. But yeah, that's what it acts as a subsampling. Okay, if you start doing the max and so on. So another thing to note is so in this case, let us say we have K1 filters, right? So we have K1 filters, M goes from 1 to K1. So that's why you see the output is also K1 matrices, okay? Because each matrix comes from the scan done by the one filter, okay, or the neuron. So that's why your output will be necessarily K1, because K1 filters scanned, okay? So output will be obviously K1. But then the next set of outputs that are going to be produced will be K2, because you are scanning these guys now with K2 number of filters, let's say, okay, at the next stage. Then the output will be K2 number of these maps, okay. So that's what decides your dimension. And obviously the way you did the convolutions and then the stride that you choose, that decides this that decides the compression that you have, or the subsampling that you have. The reduction of the image by 1 by d is decided by the d. Like even with convolution, you have seen that if you take bigger strides, then it does get compressed, right? So it gets reduced by it becomes from I to 1 by d, right? And this can also happen via pooling, right? So it could reduce by a convolution with bigger stride or by pooling, okay. So then we go to the third stage, where we have this K3, okay. So K3 number of filters we used in the third stage. This is the third stage, where so basically we can keep recursing over this, right? So we have so if I use K1 filters, then the number of output matrices will be K1. If I used K2 filters, number of outputs would be K2 matrices, and so on. So it just keeps, and then in between you do pooling and stuff. And then you can do some calculation on this. Calculations I will skip a little bit. These things are you will manage, I guess. Things are in the slides as well. Again, the fourth layer pooling we did. I mean the convolutions with the K4 number of filters, and then the pooling and so on. So basically it's repetitive, and finally we get into this fully connected, where we are doing the final classification. It could be for object detection and okay. So very briefly, this is our image, okay. This comes, let us say, with RGB. Then we choose filters. Filter number of the filter should look like have the same cylindrical shape, but with obviously same number of correspond to same number of channels. This is my K1 filter, okay. So this is my first filter, filter 1. Similarly, filter 2, okay. Now this filter will apply, right? So this guy, the first guy will act here, the second guy will act here, and the third guy will act here, okay. It produces one dot, and then it moves with some stride. This guy again is scanning with some stride. This guy is staying with some stride. It produces this output. So it will keep doing that, okay. Then we get a matrix. This is your output, right? And then second filter does the same thing. And why do we need second filter? Because second filter maybe will find out some other interesting patterns from the same area, okay. So that's why we have this multiple, just like you have multiple neurons, here also we have multiple filters scanning the same area, okay. So in this case I used total number, how many total number of filters? 2. That's why my output is 2. Now I can stack this again, just like the input image. Now this is, you repeat this like you did before. If you want to do max pooling, then you can reduce the dimension further. So let us say max pooling on 4 with stride and something like that. So let us say this is the output that you got, okay, after max pooling. So this acts like a downsampling, okay. So then you are working with this with this reduce, but you have these two matrices. So combined they are like a tensor. Now again you think of, but your filter sizes will be now like this 2, okay. You cannot have more, okay. So number of filters can change. This is a hyperparameter, how many filters I want. So let us say I use 3 in this time, Okay, so I use 3. So now this filter will start scanning, okay, with some stride and so on. So then it starts producing outputs. So this is the filter, first filter of second layer. Similarly, this produces output. This is for this guy, and similarly for this guy, 3. So now you see, now your channels become 3 now. Okay, so then again the process repeats. It's just that now your channels change, right? So your channels now change. So again, your channels change. So now you are working with 3 kind of channel. It's repetitive. It's like the previous case. And then how many filters you choose, again it depends. But this filter now you see I have to have 3. Okay, because there are 3 channels kind of. Now, but how many of these I use, that's up to me. Okay, I may go with like this. Okay, I go with 4. Okay, so then I will get 4 matrices as an output. Again, I can do pooling and so on to reduce. So this is what. So as such, it's a very simple thing. Okay, it's so there are a few things we will see. Are we allowed to do that? Like, can I change the filter sizes within the same layer? So am I supposed to have same filter sizes to scan? Should I keep the same? In Jan LeCun's Jan LeCun's LawNet, I think they didn't change. So they keep, although you can have multiple filter scanning, but they keep the same sizes. But there are variations on that. I think Google LawNet, we will see that, I guess. Google LawNet. I believe I'm supposed to say law. I believe it's French, I guess. So Google LawNet came up with different size of filters. So there was slight change in their approach. They could change the filters dimensions within the same layer. And there are many variations, and that's why we went to this architecture to see more of these. So I guess so far this is fine, and this is the end of the CNN, and then we will see variations of the CNN as a next step. Okay, so it's more about what we want to see is more about CNN engineering, like what type of changes were done. So this is what I'm saying. Jan LeCun's LawNet. This essentially brought this CNN into picture. Now it's almost the mainstream for image-related task. So this is the input image. So he was working with grayscale. So as you can see, the number of channels he has is just 1. Basically, 1 matrix is an input, and then he applies the convolutions and so on. So in fact, his network we have also seen before already. So this is the convolution C1 map. There are 6 of these 28 by 28 dimensions. Then he does subsampling. 6 of these are there, and then it's 14 by 14 size. And then he goes for convolution layer 3, 16 of them 10 by 10 size. Then he goes for subsampling, 16 of these of 5 by 5 dimensions, and then finally fully connected. So this is what was the LeCun. And then what was proposed as a improvement on this is so-called LXNet. Okay, so LXNet is another, like they give names. Okay, they come up with different variations and then they give names. So this is like the first author of this paper was, I think his name started with LX. So they propose this type of architecture. So some amount of parallelism was proposed. So here what they said is that while scanning, there are some independent blocks could be done in parallel. So this region, while one of the filter is working on this part, one of the other filter might in parallel, like at the same time. So basically they can use 2 GPUs. So one GPU runs the layer part at the top of the figure, and while the other runs the layer parts at the bottom. So that way it can reduce the time, because in those days computational resources were, even now we can say, but we are always running with the limited computational resource, and you want your network to be denser and denser. So using parallelism is one way to kind of reduce the computation time. Obviously resources, you need 2 GPUs in this case. So this is LXNet paper, and if we see here what is being used is like 5 by 5 convolutions is there. We can see 3 by 3 and then followed by max pooling, and then 3 by 3 and so on, max pooling, and then this dense, or it's called fully connected. So this is more or less the architecture, but I guess this figure is better, which I took it from Medium. Someone wrote a blog. So here you can see in more detail what is going on. Okay, so convolutions, exact details of the LXNet. So overlapping max pooling is like basically they are allowed to overlap. So this is something they prefer to use with stride of 2 and convolutions 5 by 5.
They use 0 padding. I believe this is for 2 width padding. Then overlapping max pooling convolutions, again 384 kernels they use in this case. And then 3 by 3 convolutions with 384 kernels, 3 by 3 with padding of 1 with 256 kernels, 3 by 3 with stride of 2 for overlap max pooling, and then followed by fully connected. Okay. So with this, now you can understand all these details of these architectures. You have everything in hand. So this AlexNet paper, officially, like, this is what is known by Alex. And Ilya, I think many of you already know, he's the chief scientist. I hope he's still chief scientist of OpenAI. And Jeffrey Hinton is, I believe he was his supervisor, I guess. So this was considered breakthrough. AlexNet was considered breakthrough, and ImageNet is a data set where there used to be competitions where which network can do the classification the best. So these are some of the detail. It's a deeper architecture, eight layers, 5 convolution layers, fully connected. So that was unprecedented at that time, and it could learn complex hierarchical features from the ImageNet dataset. This was one of the papers where they first used ReLU activation, rectified linear unit. So this is defined like this, max of this, and then they were also using some parallel computing. So other things where local response normalization was proposed in their paper. It's basically normalization over the local map. Okay, so I will show you a little bit about that. And then overlapping pooling is traditionally, until then, non-overlapping pooling was used, but they prefer to use overlapping pooling. Data augmentation, they also tried. So given an image, they could rotate, flip, and so on. So they increased the data set. That was part of the pre-processing step. And that helps in improving the classification. And then they did some dropouts. So dropout is when during training you just randomly remove some neurons. Okay. So these are some key ideas that they proposed in their architecture. So this is a local response normalization. This is how it looks like. So without going into too much of this, basically it says that the output that you have at the XY, you normalize it via some outputs at the nearby area. Okay, nearby n adjacent feature maps, I minus n by 2 to I plus n by 2. So basically, you sum over those values and divide by that. Okay, and few things like k, alpha, and beta are like hyperparameters. Okay, so they propose this local response normalization, but this is now kind of replaced by batch normalization in ResNets, for example. Okay, so data augmentation could be like, let us say in this case, you can just keep rotating, or sometimes you can flip the data and then you increase your training data set after having this, because it may happen that if it sees various possibilities of the rotated data, it becomes very good in training, in classifying later on with different variations of the data. So they did this initial data augmentation as well. So if AlexNet, when they ran, one of the things about CNN that I also told you before is that these filters learn features. Okay, and if you kind of plot this, these intermediate outputs that you get from the filters, you will get something like this. Okay, so these filters try to extract these features. Okay, so you can see some curves or something like that, some color features, and these are kind of, it seems like, lower level features. Okay, so these lower level features will be combined at higher level, and then you will say whether this corresponds to cat or some other image. Okay, so these small filters does kind of like visually you can see that it's learning some patterns, right, curve patterns or things like that. So these are the results of the AlexNet. So it was this is a classification challenge for image processing. So here the idea is that for a given image data set, which in this case is ImageNet, the popular colored image data set, you have multiple objects in those images, and then you will be given a training set, and then in training set you will train your CNN. In this case it's AlexNet, so the weights will get updated and things like that. And then finally they are supposed to predict what is there in the image. Okay, so this is a might. So what is the highest probability? So the softmax is giving you the probability value. So let's say in this case it's like this much probability that it's might, and then it's a container SIP. So this is the red one is the maximum probability that it is indeed and usually it's the maximum that you are going to report. So in this case, it seems like you are matching with the ground truth, which is container safe. In this case, it's motor scooter, and indeed the LXNet is also predicting highest probability of motor scooter. So it is going to kind of predict that eventually leopard and so on. So these are the results from their paper, where they showed that their architecture is very good in like classification problem. So this is the ImageNet challenge. ImageNet challenge is a data set basically, and then you're supposed to come up with an architecture. So this architecture improvement is also a research, okay, that people keep doing. They keep trying with new ideas. And since these are image data sets, then the traditional image problems like object localization, so you have to identify where is the object. So maybe you can put a bounding box and so where exactly is the object. Image classification, obviously you have to tell in the overall image what is the class of that, okay, which object is there. Object detection could be more general, that you identify multiple things within an image. So then after that came Google LearnNet. Okay, so Google LearnNet, so these are like improvements. Okay, so starting with Jan LeCun's LearnNet, and then we have LXNet, and then we have Google LearnNet. So this is 2014. So as you can see, these things are not that old, okay, compared to the usual research in other areas. This is just within a span of 10 years, things are progressing. So in here, so this was mostly done by Google. So that's why you say like even industry is actively working on this thing. So that's why they do high-end research as well by themselves. So Microsoft, Google, many of these papers you see are actually from there. So and this is a Google team, and then they they propose this. So this looks a very complicated network. It has it has many layers for sure, but they also came up with some interesting changes. So it won that classification challenge. It's called this ImageNet Large Visual Recognition Challenge. So that they won in 2014. And then one of the key idea proposed by them was something called Inception Network. Okay, so Inception is actually kind of inspired from this meme like we need to go deeper meme. And so they said this in the paper that they propose their network to be named as Inception. So in fact you can search Inception Network, and that's like Google LearnNet. So they call this Inception, and the idea behind so Inception, the idea I will explain. What they said also is that they were inspired by this paper, Network in Network. Okay, so it is not necessarily the hierarchical scanning or something. It's right there when you're doing convolution. They are saying that convolution itself is like a inner product. It's kind of a linear. Although I could have done kind of ReLU activation followed by that. Okay, but then this paper, Network in Network, proposed something like this. They said, okay, you do convolution here, but then convolution is kind of a linear operation. So they said that why not put an MLP just after the convolution, and MLP being a bit non-linear, let it express a little bit more about the convolved output. So they just put this is a minor change. Okay, so they just put this network within the network. Okay, that's what they call this. So this is the paper, Network within a network, and the Google LearnNet was inspired from that. Okay, so network within a network, and then some theoretical justifications also by Sanjeev Arora and so on. Okay, so this was the motivation behind this paper, and this is exactly what they said. So convolution filter uses generalized linear model. So basically convolution as such is an inner product and so on. So they term this as generalized linear models, extracting abstract features. So here abstraction refers to capturing features that are invariant to variations. So what they're saying is that Google works for linearly separable concepts, and then real world concepts are non-linear. Okay, and then so what they propose is like with micro networks, okay, just like in the previous picture, that can learn non-linear function and so on. And then they are saying that why they are putting this micro network, which are multi-layer perceptrons. They say this is a universal function approximator and things like that. So this is Google LearnNet, and rather than using MLP as such, the way they motivate their architecture is that first thing they do is that use different size filters. Okay, so it's like 1x1 convolution filter, size 3x3, 5x5, and then 3x3 max pooling. So the first thing itself you see is different sizes of convolutions going on. Okay, and to justify or kind of like motivate network in a network paper, they say that one by one convolution, of course, it reduces kind of dimensionality. One by one convolution reduces dimensionality across channels. Okay, so basically, it obviously it reduces the dimension of that. But so what they also claim is that network in network could be seen as one by one convolution followed by a ReLU activation. So what they said is that rather than using MLP and then doing some activation, they said that why not kind of use one by one convolution. So one by one convolution, if we have to see, then I guess this. So one by one is just one by one filter size, right? So these guys can just act on these, right? And then finally it produces just one output. Okay. So what they're saying is like, what if we could have done just one by one convolution and followed by some activation? Okay. So they're saying that it is kind of similar to doing one by one convolution. So if I'm not wrong, this is the first time they also proposed one by one convolution. Okay, usually I believe it was not usually done. Usually people will start with 3 by 3, 5 by 5, and so on. So if you look at here, right? So if you see, this is convolution blue ones. So 1 by 1, 3 by 3. Okay, and then here there is a max pooling. Okay, max pooling convolution. So again, as I see, there are multiple filters being applied here, and then there is a deep concatenate. So one of the things is like when you apply multiple shape filters, obviously the sizes of your feature map, the output after applying this will vary, right? So what will you do in that case? So then they have this deep concatenation feature that I will explain shortly. So this is more or less their architecture. Okay, they have this. So here before concatenation, all output features from the different paths must have the same spatial dimension, right? So this is usually ensured by appropriate padding. So after this, the sizes of the output may change. After this, sizes of the output may change. So you do appropriate padding of the outputs of the convolution or during the pooling. And then let us say the outputs that you get are like this. Then you basically combine these. Okay. So h times w times c1. Let us say you used c1 number of 3 by 3 filters. Then the output will be c1. And let us say this guy you have used c2 number of filters. Then this is what you get. Then what will you do, right? Because in the next set of steps you want to have the have constant number of these. So you just concatenate them and say that it's h times w times c1 plus c2, and then you start again. With the convolutions and so on. What we see here is that they make use of this one by one convolutions quite a lot. Okay, they found this very useful. And another thing that they tried is something called local classifier. Okay, they call it local classifier. So this is just one section. This is the second section of the LUNet. Okay, it was a big network. So I let us say I took the middle segment, and you can see a softmax here, right in the middle. Okay, so it's like they have added some local classifiers. Okay, so if you see here also there are like local classifier. I mean, this is at the end, right? So this is right at the end, right? But here you have another softmax going on. So it's like they have multiple classifiers. So they want to see whether there is some interesting output already at the previous layers and so on. Okay. So this is Google LUNet, and regarding one by one convolution, this is how it happens, right? So if you have one by one convolutions, and then obviously the third dimension should be 192, which should match the filter size. I mean the input one, and then when you apply 1 by 1 by 192, then what you get is in this case let's say 28 by 28, which is the initial height and width. But then you apply 32 of them, so you reduce to 32 now. So basically, a 1 by 1 convolution could be used as a reduction technique, but it does not change the height and width. Okay, that's interesting. So 28 by 28 remain 28 by 28. So if you want to do a reduction through the channels, then 1 by 1 convolution is good, because this channel got reduced 32. Previously it was 192. Okay, so this is the thing about and I have put some interesting link about some animations on how these things work, so you can check these videos later. Okay, so So this is what they have proposed, right? So network depth and width, it's a lot more now. They use 1 by 1 for dimensionality reduction and so on. That gives them good efficiency. Auxiliary classifiers, so local softmax classifiers are there, and performance. Yeah, so there are like reduced error rates and so on. So I guess that's the end of the CNN, but there is one architecture left, which is the most prominent one, which is ResNet. So ResNet I will cover in the next class, and then we will go to see how some of the engineering is done in GAN. Okay, GAN itself uses CNN. So all this that we learn will be useful there as well. Okay, thank you.